We discussed how to get the probability of a type 2 error, which you should know some textbooks will refer to that as beta. Okay? And then 1 minus beta, or 1 minus probability of a type 2 error, is called the power of a test. All right? So what we're going to discuss today are ways to increase power. Now, let's sort of remember what power is, so we're not confused at all. Yesterday, or the previous lesson, we looked at a case where mu is equal to 40, and we compared that to an alternative hypothesis that mu was greater than 40. We knew the standard deviation was 60 of the population, so we knew this is a one-sample z-test. We knew that n was equal to 1,000, and we decided to use an alpha level of 0.01. So when we went to calculate the probability of type 2 error, here's what we did. We started, like you do in every type 2 error problem, and that is to find your acceptance region. Okay, and you have to remember, if you make a type 2 error, right, don't forget what a type 2 error is. So a type 2 error means that you accept HO, or fail to reject it, usually what we say, but HO is false. Okay? That's what happens in the case of a type 2 error. So you start by finding your acceptance region. So given this set of hypotheses, we draw the normal distribution. We mark off 40 in the middle. And then we mark off our alpha level, which is 0.01. So alpha is equal to 0.01. Okay? So we had to solve backwards and figure out what x bar goes here. And then whatever that x bar is, if we're less than that x bar, then all of this green area, this 99% of area under the curve, is the acceptance region. That's the place where we would accept HO, and if we're accepting HO and we shouldn't, then we're making a type 2 error. Right. So we can get the z-score, because here's what we know. We know that this area in the red tail here, this p-value is 0.01. This area to the left is 0.99. So in your calculator, you can do the following. You can do second distributions, go to number 3, inverse norm, and type in 0.99, which is the area to the left, and you get a z-score of 2.326. Okay? And then the only thing left to do then is find x bar, but you can do that by using this. Z equals x bar minus mu over sigma divided by the square root of n. So in our case, 2.326 equals x bar minus 40 over 60 divided by the square root of 1,000. And if you solve that correctly, you're going to get x equals 44.41. So that's the x bar that will block off an upper area of 1%. So we go over here, we put in 44.41, and then last we were ready to calculate our probability. What we can say now is if x bar is less than 44.41, then we accept HO. That's what we do. Okay? All right. So then the probability of a type 2 error in this case, if the true mean equals, now we need to decide or be told that, usually we're told that, we're going to say if it equals 49, you can get this just by doing the following. The normal CDF of the acceptance region, comma 44.41, comma the new mean, comma the standard deviation. Now if you take the time to do 60 divided by the square root of 1,000, that's about 1.9. And if you do that out, you're going to get 0.007. Okay? So what does this mean is the question. Okay? So one is, it's the probability of accepting HO when in fact the true mean is 49. Right? Okay? Or it's the probability of getting an x bar less than or equal to 44.41 if the true mean is 49. So you'll notice it's very unlikely to make a type 2 error here. Power, which is equal to 1 minus that, 1 minus beta we'll call it, is 1 minus 0.007, or 0.993. That is, so this here is the probability that we won't make a type 2 error if the true mean is 49. So we'd say this test is very powerful because this power is very close to 1. All right, so let's talk about ways to increase power. So for the time being, let's just consider one thing. Suppose this problem were a little bit different. And suppose they told us to find the probability of a type 2 error if the true mean, instead of 49, was only mu equals, say, 45. So you'll notice I'm changing the problem a little bit. The only thing you'd have to do differently in your calculation is change that number to 45. So let's do that and see what we get. So second distributions, normal CDF, number 2, some very negative number, comma, the XBar, oh, that's a mistake, hold on a second, 44.41, there we go, and comma, and instead of 49, we're going to say the true mean was 45, comma, and the same standard deviation of about 1.9. Now you hit enter on that, and now you get a different probability for a type 2 error. So in the case, probability of a type 2 error, when mu is actually equal to 45, is equal to about 0.37. Yes. We can say, as the true mean, the true mu, gets further away or farther away from HO, that mu equals 40, the probability of a type 2 error goes down. And that shouldn't really surprise us. What that's really saying is, if the true mean is far away from the HO mean, then we're less likely to make a mistake and accept HO. That makes perfect sense. Okay? That also tells us that power increases. So in our list of ways to increase power, okay, so if we want power to go up, then one way to do it is to take the true mean, and it's further away. I'll just say it this way, as far away from whatever HO tells us. Mu equals 40 in this case, but it could be anything. All right. So the question is, what other things might affect this? This is saying I get it. All right, so let's just reinforce this a little bit. Look, here's the hypothesis test we performed. We thought that maybe, well, we said HO was that mu is 40, and we were comparing that versus HA, which is mu is greater than 40. Okay, so we found an acceptance region here of 44.41. That was the X bar, and anything less than that, we would have accepted HO. All right. So now consider the case where the true mean is really 45. So true mean is really 45. Here it is. Here's mu equals 45. Then the real distribution looks like this. Okay? And if you look at the area that goes with the acceptance region, it's that big. And we already showed that. That was actually about 37%. Now, let's go look at one more. Let's take this line, extend it out a little bit. Let's go to mu equals 49. So in the case of mu equals 49, when we draw that normal distribution, now what you're going to notice is this. When you get to the acceptance region, which is way over here, look at how tiny the area is for you to get in there. That area is only 0.007. So what this picture is showing us is that as the true mean moves further away from whatever HO is, there's less and less area to go with that acceptance region. And the probability of a type 2 error goes down. Extreme case. Here's an extreme case to consider. Pretend I was totally wrong about my hypotheses, and in fact, the true mean was something down here, like maybe, let's use the blue again. Let's pretend the true mean was actually 38. Well, my acceptance region is 44.41 or lower. If I draw the distribution that goes with that, you'll notice that almost all the area under this blue curve corresponds to an X bar of less than 44.41. So in that case, I would almost certainly make a type 2 error. And that's what that's really saying. Generally, you won't see things that extreme. So another thing that might affect power is the alpha level. So in this case, we did an alpha level of 0.01. Let's try and reason out what alpha levels do to power. So here we go. Here's your normal distribution. Here's the alpha level of 0.01. And that's what we used to get this problem. When we solved, we found that the XBar that goes with that is 44.41. And anything below this was our acceptance region. Okay? All right. So when we went to find the probability of a type 2 error, here's what we did. Probability type 2 equals negative something like that, 44.41, comma, the true mean, maybe it was 45, or we did 49 also, comma 1.9. And we got an answer of about 37%. Oh, hold on a second there. Okay. Now, let's change alpha. Let's think about other alphas that we usually use. So another popular value of alpha is alpha equals 0.05. Here we go. Let's draw a normal distribution again. Let's label. There it is. This is alpha equals 0.05. So here's something to think about. Think about the z-score that went with this. We found earlier in this problem that this was 2.326. So a question might be, what z-score goes with that position? So before we even go calculate this z-score down here, you can know something about it. We know up here that this z-score of 2.326 catches an area to the left of 0.99. We also know that this new z-score down here in the bottom only catches an area to the left of 0.95. So this z-score this new z-score has to be less than 2.326. And we can get it by doing the following. Second distributions, go to number 3, inverse norm, and the area to the left now is 0.95. And we hit enter, and there it is, about 1.645. 1.645. So this is a lower z-score. Let's solve backwards now. So what we can do is we can actually figure out the x-bar that goes with this. We can say 1.645 equals x-bar minus the mean of 40, because 40 is in the middle here, over the standard deviation, which is about 1.9. So we can go solve that equation. We can do that number times 1.9 and then add it to 40. Should do it. And we get about 43.12 or 42.13. So the x-bar that goes with this is smaller. It's 42.13. So you'll notice now, if I use a larger alpha level, right? Let's think about that. So a larger alpha implies a smaller acceptance region. Okay. So if you have a smaller acceptance region now, so if this is a smaller acceptance region, we should expect the probability of a type 2 error to actually go down. So let's see that. Here's how you get it. You're going to do normal CDF. The acceptance region is from here to 42.13, comma 45, comma 1.9. So let's find this new type 2 error and see what we get. So we do second distributions. Number 2, which is normal CDF, negative 10,000, something like that, comma 42.13, comma 45, comma 1.9. Looks reasonable. I hit enter, and we get a probability of about 0.065, or about 7%. So indeed, that is smaller than 37%. And we shouldn't be surprised because our acceptance region got smaller. So this is the second thing we could put on our list. All right, so far, if we're trying to make power better, number 1 is you take the true mean and make it far away from whatever HO says. Number 2, the third way is if you take alpha and you make it bigger, right? So go from something like 0.01 to 0.05, your power goes up. And that's because your probability of a type 2 error went down. Okay. There's actually one more thing that we could change that might have an effect or will have an effect on the probability of a type 2 error, and consequently, is to change n and to make n larger. Now, we're going to simplify this a little bit. I'm going to skip something, but I'll say this. We know we've been calculating our probability of type 2 errors by doing the following. We've been doing normal CDF, and we've been typing negative, some very, very negative number, comma, 44.41, comma, 45, comma, and I've been saying 1.4, not 1.9, but that's been coming from this, 60 divided by the square root of 1,000. Okay? So if you do 60 divided by the square root of 1,000, you'll get about 1.9. So if we hit enter, there's that probability of type 2 error we were getting before, right? 37%. So now watch this. I'm going to do second enter, and if I increase n, then my standard deviation is going to change. So let's say instead of having an n of 1,000, we have an n of 10,000. Okay, actually, let's be careful there. Let's put it underneath the radical. Here we go. And get rid of that extra 0. So there it is. I've increased my sample size up to 10,000. And if I hit enter now, my probability of my type 2 error just went down. And therefore, my power went up. Now, I simplified this a little bit. I should really recalculate the acceptance region, but I'm not doing it. It will still work out this way. So this is the third way. These three things are things you want to memorize or know. You'll definitely see a question about that on the AP exam.